These are the notes on trends, and we're talking about trends that we find on the periodic table, not trends in the fashion world or the world of motorcycles. We're talking about trends on the periodic table. This is obviously a follow-up to the notes on the periodic table. So in our last notes, we just got started looking at the periodic table. Today, you're going to find something you can use it for, something that you can use the periodic table to predict about a particular element that is on the periodic table. And the way that we can use a periodic table to tell us something is using a trend. A trend is a pattern that can be used to predict the characteristics and properties of an element from its position on the periodic table. So if you just find an element on the periodic table, just judging by where it is located, there are a number of things you can tell about it. And we're going to talk about some of those in these notes. Now, some of the reasons behind these will make more sense when we've talked about atomic structure, which we are going to do soon. So I'm going to be telling you what the trends are, but later we're going to learn more about the why they happen. One thing you can tell about an element based on its position on the periodic table that we've already been over is what we call its metallic character. Is it a metal? Does it have a strong metallic character? Or does it have a little bit of the properties of metals? Maybe about half of them, classified as a metalloid? Or does it have virtually none of the properties of metals, falling into the category of nonmetals? You can tell whether something is a metal or nonmetal just from its location on the periodic table. And we're going to learn why when we get into atomic structure. But there are many other things you can tell from the position of an element on the periodic table. These are called trends. Some of them are very, very good trends where the predictability is extremely high. You're going to get it right. Other times they're a little bit iffy. They don't work so perfectly. So just keep in mind some trends are better than others, but they're all useful ways of predicting properties of elements. Another trend is ionization energy. You can think of ionization energy as being how difficult is it to knock off an electron from an atom. So for some atoms, it's extremely difficult to remove one of their electrons. They're going to be kicking and screaming, never giving that electron away, and those have high ionization energies. On this sort of bar graph, the ones that are taller, the taller bars, are the ones with high ionization energy. Notice that helium is extremely high, and so is neon and argon. They are not going to be losing electrons, okay? So ionization energy, when it's extremely high, well, it's not that important when it's extremely high. That means it's just not going to happen. It's very unlikely you're going to remove an electron from helium unless you're turning it into plasma. On the other hand, as you move over, now this is not the whole periodic table, many trends can be expressed in sort of modified versions of the periodic table. Notice that this is missing a lot of the middle. You'll find a lot of trends go kind of haywire in the middle of the periodic table, so they might skip over parts of it. But if you go across the periodic table, you can see that the bar is dropping as you go to the left, lower and lower and lower. And that means that it gets easier and easier to remove an electron until you get all the way over to the ones on the left that are in yellow, that very, very first family of the periodic table, where it's super easy to take away an electron. It's not a high bar, it's a very, very low bar. So if the ones on the right, the sort of salmon colored ones, helium, neon, argon, if those are like a high wall that you'd have difficulty climbing over, then the ones on the left are like a doorstop, okay? The threshold of a door where you're entering, walking right over it. Very, very easy bar to reach. And then there's everything in between. So ionization energy is going to be something we're examining in our next lab. It's going to be one of the trends we're examining in our next lab. Another trend, kind of the million-dollar trend for understanding bonding, it's going to be a big one this quarter in Chemistry A, is what we call electronegativity. Now, I'm not going to get into right now exactly what electronegativity means. We're going to learn a lot more about that later. But the point is that it's a trend. And the trend tends toward, right there, fluorine is the highest. So notice on this table, it doesn't show everything on the periodic table. It leaves out the F block. And electronegativities are written below the symbol of the element. So notice that for fluorine, it's 4.0. And then move over to the left for oxygen, it's 3.5. And then move down, well, I've got one covered up there, right? But the one below that is 2.8 for bromine. So what do you think the one in between 4.0 and 2.8 would be? Well, it's going to be somewhere in the 3 range, right? And then look at the one covered up between boron and nitrogen. Well, that would be carbon. And its electronegativity is not revealed here. But if it's going to be between the 2.0 for boron and the 3.0 for nitrogen, what's between 2.0 and 3.0? Probably 2.5. Also look down at number 25 at manganese, which has a 1.5. And then I've got one covered up. And then to the right of it, number 27, cobalt, has a 1.9 electronegativity. So what's in between 1.5 and 1.9? You'd probably guess 1.7. And then over on the left-hand side, notice that below lithium, which has an electronegativity of 1.0, there's one covered up. And below that, we've got potassium, the K, which has 0.8. So what's in between 1.0 and 0.8? Probably 0.9. So this is what I mean about the trend. It's predictable. You can make a pretty good guess about what all of those hidden electronegativities are, even though you don't know what electronegativity is yet. Because it is a trend, it is somewhat predictable. Now let's see what the results are. Well, that one's 3.0. Well, it is between 2.8 and 4. I might have guessed something closer to 3.3, 3.4, but that's still pretty good. What about for carbon? Oh, 2.5, that's what we predicted. What about for sodium? Is 0.9, just like we predicted. And what about for iron? 1.8. So notice that even though we weren't perfectly able to predict them exactly, our guesses were pretty good because of the way that the trend changes gradually as you move across the table. Now we said that it's highest for fluorine. Do you see where electronegativity is the lowest? Where do we find it lowest on this table? Well, you might notice that some of them do not have electronegativities given. The noble gases. So you could say, well, those would be the lowest. However, there's also a place where they're unusually low. Way, way over and down. Look down to the lower left and see for cesium and francium, the electronegativity is 0.7. So generally we say that the electronegativity decreases as you head down and to the left, and it increases as you go up and to the right until you reach fluorine. And then of course you have to take into account that the noble gases are not usually assigned electronegativities, and that some of the ones at the very bottom of the periodic table, we don't have good measurements of them. We don't have good measurements of their electronegativity. So that's why those are left blank on this particular example. Then there are more complicated trends, like the trend for reactivity or activity. Well, it's a little more complicated because it depends on more than just one thing. It does depend somewhat on the ionization energy. When ionization energy is low, that tends to increase reactivity. But it also depends on electronegativity. When electronegativity is high, that also increases reactivity. So reactivity is one of those trends that isn't quite as clear-cut. It just doesn't move in one direction across the whole table. And this is one that we'll be looking at in our next lab. We'll be looking for the trend in reactivity. And I'll just tell you now that it's not a super obvious trend. It's one of the trickier trends that you're going to be looking for. If you pay close attention later on, there's probably a few hints I'm going to give you that might help you locate that trend. You can tell a lot about electrons by looking at the periodic table. We're about to go into atomic structure, and you'll learn a lot about that. But let me just say at this point that the reason the periodic table has that weird shape and structure, why it's not just all lined up in a nice little rectangle, is because of electrons. And you may have noticed that my periodic table that I'm showing you here varies a little bit from some of the other periodic tables you might sometimes find, like in places in the textbook. They actually do have this one in the textbook. This is the first textbook where I've actually seen that included, but it doesn't always do that. There's a little section there that is sometimes left out, or it is cut out and dropped to the bottom. They do this to save space, but just make no mistake, this is the actual structure of the periodic table. This is the correct form. And then the other version I like to call the chopped form. If you look at the chopped form, the F block, what we call the F block, is thrown down to the bottom. Well, that can cause a number of difficulties when you're figuring things out, as you're going to see in our next section, okay? So the reason we call them blocks is because that is which orbital is being filled. You're going to find that out very shortly. And if you want to know what I mean by blocks, well, picture blocks like this. These are little building blocks. These are my son's building blocks that I found a few that looked roughly like the shape of the blocks on the periodic table. So see that green block located there? Well, a lot of times they drop that one down to the bottom and slide the yellow one over next to the blue one. And that is mostly to save space. Otherwise, you'd have a big blank area. And so that they can write the elements larger, kind of magnify them. But this is really where it goes, and it makes a big difference, as you're going to see, with electron orbitals to put it in the right place. So the electron orbitals are parts of the atomic structure that we are going to learn about. So even not knowing what they even are, you can sort of see where the s orbital is being filled just by the s block, where the f orbital is being filled by the f block, where the d orbital is being filled by the d block, and where the p orbital is being filled by the p block. So now there's no exceptions to this except for one little one that you can see by color coding here. Notice way up on the right, you've got helium, which is in the wrong location, and we're going to explain why that is when we go through the electron orbitals. But the point is that this is like a trend on the periodic table. You can tell which electron orbital is being filled even if you knew nothing else about electron orbitals, just by its location on the periodic table. Other trends that we find on the periodic table are obviously atomic number. That is a perfect trend. It is invariable all the way through. And atomic mass, which is almost as good, but there are exceptions. There's several elements that defy the trend for atomic mass, at least a little bit. But the number one trend that helps you understand the properties of elements and actually all the other trends is the size of the atom. The number one trend I want you to try to understand is about the size of the atom. So I'm going to talk about it briefly here, and then we'll get back to it once we've talked about atomic structure to understand why it happens. So the atomic size trend is a pattern that repeats over and over, okay, kind of like a roller coaster going up and then back down and then up again even higher and back down. It's a pattern that repeats as you go across the periodic table. This size trend is critical for understanding reactivity, why things are metals or nonmetals, and many, many, many other properties like electronegativity. So the atomic size trend, I would have to say, is the most crucial trend to try to understand. But it's not easy to understand it. And I can't even fully explain it to you at this point because we have to go into some detail about atomic structure first. But I do want to talk about what the trend is at this point. The trend is that we generally get larger atoms on the left side of the periodic table. Now notice this is the chopped periodic table, even more than that. I'm leaving out some of the ones on the bottom as well, some of the ones on the lower period, what we call periods of the periodic table. So notice that these look like, someone commented to me that this looks like M&Ms, like candy. The ones on the left side just generally are larger. Also, the ones near the bottom are generally larger. As you move over toward the right, for the most part, it's not a perfect thing, but they get smaller, okay? Now this is an interesting property of elements as you go through the periodic table. They often get smaller as you move to the right. This is one reason that we find the nonmetals on the right. This is also the reason we find the metals on the left and the bottom, because the metals tend to be the bigger atoms. And we'll understand why that matters when we talk about metallic bonds, and we'll understand why this pattern occurs after we talk a little bit more about atomic structure. This trend isn't super obvious in this picture, I know, but if I chop out what we call the D block as well, this is an even more chopped periodic table that you don't usually see, well then the trend becomes much, much more obvious. So notice that in general, we've got larger atoms on the left side, and then as you go across in one particular row, one period as we call it, they get smaller. And then the same thing goes in the next period. As you go across from left to right, they get smaller. And in the next period, I'm zeroing in on this section of the periodic table, chopping out the D and the F block, and only going down to what we call the fourth period, just to make sure this trend is more obvious. But this is a very important trend, like I said, determines if something is a metal or non-metal, determines ionization energy, electronegativity, all kinds of things. Basically, all the other trends depend on this one. So now that we've discussed what a trend is and given a few examples, I'm going to do a quick run through of the different groups that I am going to highlight in my class on the periodic table. Now, there are many, many groupings on the periodic table, and I'm not saying the ones I'm not mentioning are not important, but these are the ones through which we can get a rudimentary understanding of chemistry. These are the ones that I'm going to emphasize. So here we go. The alkali metals. The alkali metals is the very first column in the periodic table, not including hydrogen that is above them. This is a very important family, and you are going to see examples of how they react in the demos for the lab we're going to do next. Next to them, we have the alkaline earth metals. Now notice that it sounds very similar. The other one was alkali. This one is alkaline earth. So they're very similar, and they have very interesting properties. They're kind of famous for the way they react, just like the alkali metals, you'll see. And they're often given short shrift. They're often overlooked because they're right next to a very dramatic family, and they're a little bit less dramatic. So we don't focus as much on the alkaline earth metals, but they will get their day in the sun. We will focus on them at least a little bit later on. Then we have what are called the rare earth metals. In basic high school chemistry, we don't generally even get to these. We might mention some of them, especially uranium. We might mention some of their properties, like radioactivity and things along those lines, but we just don't have enough time to focus on these elements, which, just like their name says, are very rare. So they don't play a huge part in everyday chemistry. Then we have what we call the transition metals. These metals are transitioning from the alkali and the alkaline earth metals to what we call the main group metals, as you're going to see, and they all kind of have similar properties. Many of these metals are very colorful, and they have many, many things in common. There is a subgroup within the transition metals. It is part of the transition metals that I like to emphasize. A lot of times this subgroup is neglected in high school chemistry, but I think it really helps with your understanding, and that group is the noble metals. Now notice, this is a smaller group within the transition metals. The noble metals are the metals that we can sometimes find in their pure state. So that is why they are called noble, because they often don't react with other elements, and so you can just find them lying around in their pure state. This includes silver and gold, which you can find up in the mountains, like the California Gold Rush. They found gold just washing out of the eroding mountain in the rivers, and that's because it's a noble metal. And we'll be discussing those later. So there are several noble metals. Some of them are more noble than others. You would have to say that platinum is the most noble of these. Then we've got the main group metals. These are still metals, but these are found way over on the right side of the periodic table in what we call the P block. Okay, so notice that these metals are kind of getting further and further to the right as you go down. They're sort of on the march, sort of taking over the periodic table. And there's a reason for this. It has to do with atomic size. Turns out if you're a bigger atom, you're more likely to be a metal than a nonmetal. And there's many interesting elements in this main group metals category, like aluminum and tin and lead. Interestingly, aluminum and tin often get switched around in our nomenclature. Sometimes we call aluminum foil tin foil. Okay, sometimes we have aluminum cans and we have tin cans, and sometimes the names will get a little blurry there. So there's a lot of interesting metals in that group as well. Then there's a family called the halogens, also pronounced halogen, which is why I've shown the halo above them, a very, very important and reactive family on the periodic table that we will be discussing quite a bit for understanding chemistry. Right next to these, we've got the noble gases. Well, the noble gases, kind of like we just said the noble metals, they don't react much. Okay, in fact, the noble gases are the least reactive elements on the whole periodic table, but we can learn a lot about chemistry by studying them. Even though they don't get involved in many chemical reactions, understanding them is kind of like the basis of chemistry, the basis of understanding stability. So putting all those together, and there are more we will talk about, but those are the basic groups we're going to emphasize, you can really get an understanding of chemistry from those. Okay, some of them we'll discuss more than others. Like I said, the rare earth metals, they're not going to come up too much. You just got to be aware that that's where they're located. So those are a few things about the periodic table. Other things are going to have to wait until we learn more about atomic structure. Once we've done that, we will revisit some of these trends to understand why they happen. We also have trends on the periodic table of the antimatter elements, but this is a very easy trend no matter which one you're talking about, because at this point we've only managed to synthesize and observe two antimatter elements, anti-hydrogen and anti-helium. These are real and they can be synthesized. So a trend on this periodic table would either be to the left, increasing to the left, or increasing to the right. That's pretty much all you get. And so one I'll give you is the reactivity on the antimatter periodic table increases to the left. How about that? I think that's all I'm going to say about antimatter right now. So those are the end of the notes on trends, and we will continue understanding these trends as we go forward. Once we've learned more about atomic structure, we will understand the why. Why are these trends happening? Thank you.